Welcome students. This is Shantikla, Assistant Professor from Department of Artificial Intelligence and Data Science from Ramco Institute of Technology. Today we are going to see about the topic Spark Streaming. Before entering into the topic, we just see about the agenda for this video. First, what is Spark Streaming? Why Spark Streaming? Framework for Spark Streaming, drawbacks for Spark Streaming, structure Spark Streaming, framework for Spark structure streaming, output modes, advantages, window operations on event time, handling late data using watermarking, joins, stream inner joins, outer joins, and overview of stream inner joins. First of all, we are going to see about Spark streaming. Before entering the topic, we just see about the need for Spark streaming. Spark streaming is needed for processing and analyzing live data stream in a scalable, fault-tolerant manner. It enables real-time analytics, machine learning on streaming data, and data integration tasks. Many important applications must process large streams of live data and provide results in near real time. For example, social network trends, website statistics, intrusion detection systems, etc. require low latency for faster processing. Next, we are going to see about what Spark Streaming. Spark Streaming is an extension of the core Spark API that allows data engineers and data science to process real-time data from various sources, including but not limited to Kafka, Plum, and Amazon ICs. This processed data can be pushed out to file systems, databases, and live dashboards. Framework for large-scale stream processing scales to 100 seconds of nodes can achieve second-scale latencies, integrates with Spark batch and interactive processing, provides a simple batch-like API for implementing complex algorithms, can absorb live data streams from Kafka, Flume, and ZeroMQ, etc. And next, framework for Spark Streaming. Spark Streaming provides a high-level abstraction called a discretized stream or D-stream, which represents a continuous stream of data. These streams can be created either from input data streams from sources such as Kafka, NICEs, or by applying high-level operations on other D streams. Internally, D streams is represented as a sequence of RDDs. Now we are going to see about what is RDD, resilient distributed data set. Spark introduced the concept of RDD, an immutable fault-tolerant distributed collection of objects that can be operated on in parallel. RDD can contain any type of object and is created by loading an external data set or distributing the collection from the driver program. RDD supports two types of operations. First one is transformation, how to transform one data collection into another, such as map, filter join, union, and so on, that are performed on an RDD and which yield a new RDD containing the result. Means create a new data set from exiting one. And another operation for this is actions requires that the computation to be performed, such as reduce, count, first, collect, save, and so on, that returns a value after running a computation on RDD. And the main drawbacks of Spark streaming is handling state for long time and efficiently is a challenge in these systems. Lambda architecture forces the duplication of efforts in stream and batch, as the API is limited doing any kind of complex operations takes a lot of effort. No clear abstractions for handling stream-specific interaction like late events, event time, state recovery, etc. To overcome this drawbacks of Spark streaming, we are moving to structured Spark streaming. In structured streaming, a stream is modeled as an infinite table, infinite data set. As we are using structured abstraction, it is called a structured streaming API. All input sources, stream transformations, and output strings model as data set. As data set is underlying abstractions, stream transformations are represented using SQL and dataset DSL. The main idea behind structured streaming is that the data continuously being appended to the table. That is, in simplest way, structured streaming in your data frame, but streaming. Apache Spark Structure Streaming is a leading framework for processing real-time data streams. Its flexibility, scalability, and integration capabilities make it essential for modern data engineering. This is the framework for Spark structured streaming. The key idea in structured streaming is to treat a live data stream as a table that is being continuously appended. This leads to a new stream processing model that is very similar to a batch processing model. You will express your streaming computation as a standard batch, like a query as a static table, and Spark runs is an incremental query on the unbounded input table. Let us understand this model in more detail. So in this model, we have three output modes. First one is complete mode. The entire updated result table will be returned to the external storage. It is up to the storage connector to decide how to handle writing of the entire table. The next mode is append mode. Only the new rows appended in the result table, since the last trigger will be returned to the external storage. This is applicable only on the queries where existing rows in the result table are not expected to change. Update mode, only the rows that were updated in the result table, since the last trigger will be returned to the external storage. And the main advantages for this is Spark's structured streaming handles even time and late data. It is fault tolerant semantics using source and sink, scalable to handle large data sets and high processing loads, making it suitable for various big data applications. Provides a wide range of analytics capabilities, including machine learning and graph processing and SQL processing with the help of Spark SQL. Supports various data formats and source, including HDFS, S3, Kafka, Parquet, and JSON. And the next important thing is window operations on event time. See this, the diagram without window means the data can be classified or categorized into batches. But in window-based operations, the data can be grouped into a window. Windowing is a technique associated with the stream processing, especially stateful stream processing. It is used to divide a continuous data streams into smaller finite chunks called streaming windows. Dividing a stream into windows happens based on certain criteria. These criteria can be time-based, for example, 5-minute intervals, and count-based, example, every 1,000 messages, or even based on the data characteristics. For instance, changes in data volume among them. Time windows are by far the most commonly used. In structured streaming, data is processed window by window instead of batch by batch. This handles out of order with the help of timestamps attached with the original data. And then late data, with the help of watermarking, we can handle the late data. Watermark tracks a point in time before which it is assumed no more late events are supposed to arrive. It handles the late data. When working with a multiple structure streaming inputs, you can set multiple watermarks to control tolerance thresholds for late arriving data. Configuring watermarks allows you to control state information and impacts latency. A streaming query can have multiple input streams that are unified and are joined together. Each of the input streams can have a different threshold of late data that needs to be tolerated for stateful operations. This diagram will explain the given topic. And the next we are going to see about the joins. Spark supports the following different types of joins. Static to static joins. In this static to static joins, we have an inner join, left outer join, right outer join, and full outer join. These all types of joins are supported in static and static. And stream joins with static data, only inner joins alone supported. And stream to stream joins, full outer join is not supported. We will do a deeper dive into streams to stream joins in the following slides. Stream to stream inner joins, a simple inner join need to buffer all the paths even as a state. A match can come on the other stream anytime in the future. This can be time consuming. Inner join with watermark and time constraints. Time constraints need to be provided so that buffer events can be dropped. We take the example of admonitations. We need 3 watermarks in total, one for each stream and third for associating each click with impression. As it is not necessary that a user will click on the ad as soon as it appears. Outer joins, next we are going to see about outer joins. Time constraints and watermarks are necessary for left, outer and right join. In case of right outer join, it is necessary for us to give a watermark for the left stream, vice versa for left outer join. Outer joins, it may be a left, right, and full outer joins are available when you need to capture a record from one stream that don't have a match in the other, effectively generating null values for unmatched fields. For outer joins, need to combine watermarks with a time range conditions within the joint condition. This helps the system determine when to emit null values for unmatched records and when to consider a record late. Overview of stream joins. Inner optional specify watermark on both sides. Time constraints for state cleanup. Left outer watermarks must be specified on the right plus time constraints for correct results. Optionally specify watermark on left for the state cleanup. Right outer watermark must be specified on the left plus time constraints for correct results. Optionally specify the watermark on right for all state cleanup. Full outer join. This will not supported in stream to stream joins. Okay, students, thank you so much for watching this video. Thank you once again.